Hey, thank you all for coming. Just to kind of give you a background of who I am, what I do, and how I got to where I am now. I'm from Illinois State University. I had a bachelor's in chemistry and a bachelor's in environmental health. I've been working here at ISTC for about 10 years. My first 4 to 5 years I was doing elemental analysis, and then after that I moved into the organic group and did organic analysis. So about 4 months ago, Kishore came into my office and he told me that he was really interested in this thing called aqueous phase. And in the past, it's always been, we've always known what we're looking for. But the difficulty with the aqueous phase from thermochemical conversion is we really don't know what's in there. So not only do we have a hard time figuring out how much of what's in there, but also what it is in the first place. So yes, I do call this phase 1 nitrogen compounds, but I should actually call this phase 1 part 1 because it's going to turn into quite a large ordeal. So for thermochemical processes, this is kind of a flow diagram, and this would be applicable to hydrothermal liquefaction or pyrolysis. Either platform would work here. But however, you have algae production and coupled with a wastewater treatment, and then you would do thermochemical conversion on the biomass. And what you get is 4 products. You get biogas, bio-oil, biochar, and an aqueous phase. Now, for the most part, these guys are pretty well characterized. We have a pretty good grasp of what's in them. However, the aqueous phase, there's really not much information out there. It's just basically a complex mixture of carbon, nitrogen, hydrogen, and oxygen. And do you guys know how many different ways you can hook these 4 elements together? How many? I knew you'd know that one. You know that one. So yes, it's remarkable how many different compounds you can get there. So I do dabble in a little bit of this. I do dabble in a little bit of this, but right now my focus is right here. So this aqueous phase, currently people want to use it to grow algae. It has a high ammonia content or nitrogen content, and it would be ideal for fertilizer. And but right now it's inhibitory to algae. If you try to grow algae directly in it, it basically kills it. So you would have to treat it somehow before you can feed it back into the loop here. And also, what is the environmental impact of this aqueous phase? We really don't know what it is, and if we're starting to make a lot of it, we should kind of try to figure out, what it is and how to deal with it. Okay. So Derek and Grant Blazina did a hydrothermal liquefaction here at ISTC, and the feedstock that I focused on is spirulina, is the genus, and these are their conditions. And they basically got their aqueous phase just by in a separatory funnel. They separated it from the oil and then filtered it through a membrane. So we went to the literature to see what was out there in the literature, and you could see that nitrogen it's about 2 to 1, nitrogen to carbon ratio for the aqueous phase. And this is the distribution throughout all the products, and you can see that 35% of the nitrogen ends up in the aqueous phase. And then this is a GCMS general scan of a different species. However, we use this to get an idea of what kind of nitrogen-containing compounds we would be up against. So I just want to note, though, this is a general scan. General scans are very prone to error. They just use a library search, and they're yes?
How do you extract something out of water?
That's a good question, too. How do you separate the methanol from the water after the extract? I've wondered the same thing. So I didn't do it that way, but you're absolutely right. So this is kind of also the other thing important here is they just report a percent area, the chromatogram. It really has no bearing on what the actual concentrations of these compounds are. But it's a place to start. When you don't know what you're up against, general scan is the first place to start. Okay, so we found a reference method. Actually, Kishore once again comes in my office with a stack of papers of methods for nitrogen compounds, and we found the simplest one, and it appeared to be the most effective, was for heteroaromatic compounds from contaminated groundwater. And it's just a real simple liquid extraction with dichloromethane. Concentrate it to 1 ml final volume. And then these are the recoveries for the nitrogen compounds and sulfur and oxygen compounds in their study. So they had pretty good recoveries. So very simple, fast method. All right, so we performed that method, and then what we did is we sent a feed sample out for nitrogen analysis to Midwest Labs, and then also we did TOC analysis here at ISTC. And then also we sent out the water left over after we extracted it, so that we were able to get an idea of how much of the total nitrogen and carbon that we had extracted. And unfortunately, it's only 4.2%. So we only extracted 4.2% of the organic nitrogen in the sample, and there's a lot left over. So, but hey, it's what we started, what we have to work with, and that's where we started. And also, we got about 3.5% of the total organic carbon extracted in our extract. So then, also I followed their GC gas chromatograph parameters from that paper. This is my operating parameters, the column, my oven ramp. We ran it on two different instruments. We ran it first on a nitrogen phosphorus detector, thermionic detector. It's specific to nitrogen and phosphorus. And then also we ran it on our high-resolution magnetic sector, GCMS. That's this beast right here. This is a chromatogram of a 5-fold dilution of my extract, and I have 205 individual nitrogen compounds. That's a lot. It's a lot to deal with. So what I did is I just diluted it 100-fold, and now I got 97. So these are the 97 peaks that I'm going to focus on. The nitrogen detector will tell me where the nitrogen compounds are at, and that's what I use that for. I use it like a guide. Then I run it by GCMS mass spec, and here's my general scan of the same sample. Okay, and you can see right here, this peak here at 10.89 corresponds to this largest peak right here in the nitrogen chromatogram. All right, so that's the one I want to focus on first. I might as well start with the biggest peak. This is kind of neat. This is a general scan map, and this is another way to look at that general scan, except for now we have our retention time here. We have our mass range here, because I looked at all the masses from 35 to 200. And then the intensity of these colors here, going from blue to red, is most intense. So those are where the most intense ions show up. And you can kind of see there's a cluster here and a cluster here. So it's a quick way to look at all the masses in one place. Okay? Any questions on this? All right. Intensity, that's right. So blue is the least and red's the most. And this also gives me an idea where I should focus when I'm looking at this data. Okay, so so we're starting off with this biggest peak, and there it is. It's a 10.89 in the general scan, and it's right here in the map. So there's this wonderful software available at NIST. It's called AMDIST, and it was designed for chemical weapons testing. And it's a deconvolution software. And what it does is it filters out colluders with the peaks, and it kind of removes a lot of the background and gives you a lot cleaner mass spectrum. So we ran the mass spectrum of this peak through AMDIST, and I know it has nitrogen. So I told the library search to only look for carbon, hydrogen, and nitrogen compounds. And this is what I got. 1-methylpyridine. Okay? However, we don't have oxygen here. So I did another search. However, the next search I did was CHNO. And then I get to pyridinone. Sorry, I'm still working on the names, but pyridinone, 2-pyridinone. And so those are my two most favorite hits in the library search with these nitrogen constraints. So then I looked at the mass spectra, and this is the mass spectra from 1-methylpyridine. And you can see here's the formula, and it has an accurate mass of 99.1048. And that accurate mass is going to come in handy later. You'll see why. There's the molecular ion right there, 99. So here's the mass spectrum of 2-pyridinone, and it also has the molecular ions right there at 99, and it has a formula of C5H9NO, an accurate mass of 99.0684. Okay? So when you compare the two mass spectrums, they're very similar. You can see that these peaks are very similar. And when you overlay it with the map, you can see at that time, 10.89, you have intensities that pretty much match that. But I still can't split the two. Okay? So now what we can do is, lower resolution mass spec, you can see that the peaks are very similar. However, with high resolution, we can actually split that 99. This 99 is actually 99.1048. And it corresponds to this formula here. This 99 is 99.0684. And it corresponds to this formula here. And we could do the same thing with the fragments, too. So not only can we do an accurate mass for the molecular ion, but also the fragments. So what I did next is I run the high resolution mass spec at 99.0684 and 99.1048. And you can see that a peak appears for C5H9NO. So I've just ID'd that compound. So then what I do is I go out and I buy some 2-pyridinone. I make a calibration curve. Here's a 10 milligram per liter standard. I run a HCl extract. I just diluted it 100 times fold. And then I also ran an extract spiked with 2-pyridinone. And I got about 93% recovery. So I just quantitated one compound out of 205. And, Tom over here is kind of wondering what this peak here is at 9.13 is, and it's actually another compound with the same formula as 2-pyridinone. And it's 1-methyl-2-pyrolindenone, 2-pyrolindenone. So it has the exact same formula, and it was in my spiking solution. So that's why it showed up there. Okay. Questions about how I did that? No? Okay. That I don't know yet. I haven't looked it up. I haven't gotten there. Why don't you do that for me, Wei? Tell me. So, was that fun? One down, 204 more to go. So let's do another one real quick, just to kind of rehash. So now we know that this peak here is 2-pyridinone. So now let's go after the second most strongest peak. Okay. Let's see. So AMDIST search with NIST really likes 1-methyl-pyrrolindene with CHN constraints. And then if I do CHNO constraints, it really, really, really likes 2-pyrolindenone. Okay? I throw it up on the map. Here, too, the mass spectra are similar. However, see this 57? It's a lot more intense. This 42, 57, 84 have intensities that are pretty darn similar, whereas this 42, 56 is low, 85 is high. So then when you look at the map, if this was the right compound, you would expect these intensities to be pretty close, but they're not. Actually, this 56 looks a lot less than the 84, 85, or 42. Okay? So the other thing I love about this picture is you see here that there's no ions above 85. However, in the map, there's something right there at 95. There's a coallure lurking. So I haven't figured out what it is yet, but I'm going to look into it. But I just think that's neat. So next is we go to the high-resolution measurement, C4H7NO, which corresponds to 2-pyrolindenone. And the other compound, there's no peak. So we've ID'd that peak. Go out and buy some standards, make a cal curve, dilute the sample, do a spike, got a 94% recovery, and we've just quantitated 2. It's 2 out of 205. Okay? So I turn this crank 8 more times, and this is what I get right now for results. However, I do want to go back and remeasure 1-methyl-2-pyrolindenone. My spike didn't recover well, so I don't feel comfortable reporting a number yet. And pyridine is actually really low, and I have to go back and rerun it because it was below my detection limit. But I have 6 compounds quantitated for the aqueous phase right now. 2-pyridinone is the most concentrated at 30. 2-pyrolindenone is the second most at 14. And judging from the nitrogen chromatograph that we saw earlier, those are the 2 most concentrated nitrogen compounds in this aqueous phase. Okay? All right. So now, this is kind of our flow chart. Go ahead, BK.
The nitrogen and carbon that you extracted, 4% and 6%, is it matching with what you had initially?
This is 4% of 4%. So because there's so many nitrogen compounds there, that's why we've only picked up 4%. So these are based on these compounds, correct. So it's 4% of 4%. It's very little, but it's a start. Go ahead, Sheldon.
So when you do a search for elemental composition,
Yes.
you think about nitrogen, carbon, and hydrogen, right? And oxygen.
Yes.
I think for a lot of organic molecular, we could have chloride, phosphorus. Did you think about that?
Yeah, but there's not much chloride in the, there shouldn't be much halogenated compounds in the material because the feedstock shouldn't have, you guys are the expert, is there a lot of halides in the algae? Yeah, I think that there's not much halides. So.
Thing is like for the organic molecular, there should be like 10 to 15 major elements you should search. And right now you only search 4, so I think you probably should expand that search.
Okay. Sure.
I just
Sure, but I mean, it's a place to start. If I expand that search, I'm going to get more compounds, and I got to start somewhere. But you're saying expand my elemental list, get away from just carbon, nitrogen, hydrogen, oxygen? Sure. I would love to do sulfur. Yeah, yeah. We'll get to that. So this is kind of our flow chart. Definitely, we need to work on this. We need to work on the sample prep because we've only extracted about 4% of the total organic nitrogen. So we're going to go back and definitely do a much better job on that. So then, yeah, nitrogen analysis by GCNPD to give us an idea where the nitrogen compounds are at, compare it to general scan, GCMS data, then do AMDIS deconvolution, library search, use the general scan just to kind of get an idea of does it make sense, and kind of go back and check AMDIS against the raw data. Confirmation by high-res GCMS, and then SIR stands for selected ion recording. Also, you might have heard it called selected ion monitoring, SIM, SIS, selected ion storage. They're all techniques that will only select certain ions and throw everything else away. So they're a lot more sensitive. But then, yeah, ultimately, this is where you want to go. You want to get a reference material, calibrate. But then something interesting happens. After you get reference materials, you can create something called a retention index. So that's what I'm going to do next here, is now that I bought standards, I'm going to program AMDIST with these standards. So then now not only are we looking at mass spectra data, but we're also looking at boiling point data. It takes that into consideration. So then I create an NPD, nitrogen phosphorus detector retention time table for the 97 compounds that we saw at 100x dilution. And I calculate the relative retention time to 2-pyridinone because I can't actually get the retention times from the mass spec and the NPD data to line up perfectly. And I have a good idea why. But to get around that, I calculate relative retention times. Then I compare it to the general scan data. And all these RRs here are relative retention times that match the NPD data. All right? Then I do library searches 4 different ways. I do 2 of them, just general scan, just straight up library search. And then I do 2 with AMDIST, CHN constraints, and then CHNO constraints. And everything in yellow here is something I'm slated right now to do a high-resolution measurement of. Everything in red is something I've already done a high-resolution measurement, and I've identified them. So the next step would be go out and buy the reference materials, if I can. Some of these compounds, I don't know if I can get the reference materials. So yeah, these are the compounds I got slated for high resolution. Basically, after I do these measurements, this list will basically be cut in half because most of these are 2 of my top matches that I'm trying to eliminate one and pick the other. Like I said, these are the compounds that I identified by high resolution measurements, and I think these guys I should be able to get standards for. These guys, I'm not sure yet. And it's kind of interesting. Let's go all the way back to the map, this big map here. And what we see is it's about what you'd expect at a low retention time. You have low molecular weight, and as a higher retention time, your molecular weight increases. So these compounds here are all pretty simple, and they'll be easy to get. However, what we're starting to see here is larger compounds and variations on repeating themes. And you can kind of see that if you look at these intensities right here. They follow the same kind of mass pattern. God, I love this thing. It's awesome. Okay. So then, just to kind of wet your palate, I want to show you the profile of HTL from 4 different feedstocks. So what we've been working on here is the spirulina, but here's waste coffee grounds. Totally different. And I'm convinced there's some super caffeine molecule there that's going to be rich and famous. This is Dimorphos is the feedstock, the algae. And you can see it's a lot more complicated than spirulina. So I just can't wait to do that one. This is the HTL aqueous phase from soy soap stock. And you can see, a lot different nitrogen profile. So there's plenty of work to be done there. This is, I don't want to tell you about this yet, because this is a secret weapon that I'm kind of still working on. But these are high-resolution nitrogen measurements of 2 different platforms, pyrolysis and HTL, of the same feedstock. And you can see that there is similarities, yet there is differences too. So it's feedstock dependent, and it's very the processing condition dependent as well. Here's another one that I'm very excited about. My colleague Xin Ying did this one, and this is a RO membrane filtration of the aqueous phase. And these are 5-fold dilutions. This is the feed. This is the redentate, and this is neat. This is a neat injection, and you can see that he's removed a lot of the nitrogen compounds. And if you look at the scale here, this is about 20 picoamps, and this right here looks like about maybe 200 picoamps. So he did a good job of removing a lot of the nitrogen. So it'll be interesting to see which ones made it through. So we can modify the membrane and do experiments like that. So basically the summary is that we now have a systematic approach for characterizing nitrogen-containing compounds in a complex mixture, in a complex matrix. So we've developed the method for identifying an unknowns. And DCM extract from spirulina is a complex mixture, and the most concentrated nitrogen compounds are 2-pyridinone and 2-pyrolindenone. And the nitrogen profile is very feedstock dependent, and it's processing condition dependent. So where do we go? Well, I still have a lot of work to do in just characterizing this little extract that I have. I still have, let's see, I had 40, 850, about 150 more peaks to figure out. So I got a lot of work to do with that. We also need to work on our sample preparation methods. We need to extract more of that organic nitrogen, and we need to fractionate it. So that's definitely something that we're going to start doing right away. Then we can extend and refine these developed techniques to other matrices, such as biochar, bio-oil, etc. And then we can apply these problem-solving methods to anything associated with thermochemical conversion, oil refining, upgrading, water treatment, and God only knows what other applications. So, and there's my references. Questions? Doubts? Go ahead.
These things look like they come from protein.
That's
degradation of proteins.
yeah. That's what we need to look next. Absolutely, that would, because this is a high protein content feedstock. Correct.
A lot of them look like flavor compounds.
Yes, I've noticed
Cooking.
exactly. When I looked at the databases for the mass spec, I seen a lot of the compounds come from food science area, like people grilling and overcooking their steaks and getting carcinogens from it. So yes, definitely. But that's somewhere I will look. And in fact, I even thought about maybe trying to go over to the proteomics department, the guys that do proteomics on campus, and see if they can help me maybe time of flight analyses on this, because that would be nice if I can get all the high resolution measurements. That would really help me a lot. Any other questions? Go ahead, Wei.
You folks liquid phase, right?
Yes, aqueous phase.
You mentioned nitrogen only less than 4%.
Is what we extracted. 4% of the total organic nitrogen.
So where is left? Mostly in the char or in oil?
Oh, no. Let me back up. Okay. right here.